Welcome back, DC Circuit students. This is the second video in our calculations section on square wave behavior of an RC transient in a switching circuit. So in our first video, if we want to look over here, and I'll switch colors. In our first video, we took a look at this circuit that has two voltage sources in opposite directions. Oriented opposite directions, so positive, positive here. And at first we left this switch to this kind of opposite oriented backwards battery. We left it open and we closed the first switch. And then we looked at the effect of that closure and the current flow and the time-dependent charging of our capacitor to get an expression for what we would see on our oscilloscope if we looked at the voltage drop over the capacitor. If we took this measurement in a circuit that we built and we plotted it, what would we see? And we concluded, we derived a nice expression for time-dependent voltage as an exponential function of time with RC equaling the time constant. So now we're going to switch over, we're going to use aqua to show that we're kind of at a different part of our square wave. So if we had a way to just do a single step function, we could actually measure that green curve. But as it turns out, when we apply a step function to a periodic step function, a square wave function to our circuit, we're just going to get the whole amplitude of the curve. In this case, if I were to apply a square wave with an amplitude of E, I would just get this. And that first initial charging would kind of be lost. So what I'll be able to measure is really, I would be looking at for practical purposes, my time equals 0 as this point up here that I'm kind of making a bigger and bigger dot for. And I would be looking at the voltage drop over the capacitor as doing, I would expect it to do something like this and reach steady state. So I don't have 0 to E. What I have is from E to negative E. Because the capacitor is already charged at this new kind of time 0. And so what I'd like to do is do a little bit of a derivation of what I would expect for a time versus V sub C in terms of whatever my my E and my R and C are. Excuse me, and then apply that to what if the time was equal to the product of R and C, meaning T equals tau, what voltage I would expect, and that way I can look at my plotted experimental curve, which I'll be getting something like this, and I can verify my time constant with a measurement, or I can look at a measurement for a circuit where maybe I don't know R and C, and I can identify the time constant and then maybe figure out how I want to change R or C to adjust it if I want to. So if I'm going to start with that, I'm going to use the same exact procedure that I did. I'm going to write down, first I'm going to show that I've closed the switch, closing the switch. And in fact, I'm going to make sure I show that as open. Okay. And I'm going to write down my initial conditions. I'm going to show the battery, or I'm going to show the capacitor all charged up. Okay. So I'm just going to reiterate that the charge on my capacitor at any time is equal to whatever V sub C is times C, and the voltage drop over my resistor, of course, is going to be current times the resistance. But in this case, I'm going to start looking at signs. So I'm going to just put a question mark here. I know it's IR, but now I need to think about the sign of the current and the voltage drop in which direction. So I'm going to start with my KVL expression. I'm just going to say we gotta look at KVL here. So I'm going to start over here at ground again. So that's 0 volts at ground, and I'm going to come up through this voltage source, except it's backwards. So as I go from this point at ground to, we'll call it node A here, I'm going to be subtracting E. I'm going to be below ground here. I'm going to go from A to B. So as I go from A to B, I'm either going to add or subtract the voltage drop over the resistor. So this is a bit like some of our network analysis, where we have to know which direction the current is flowing to know, are we basically swimming upstream against the current, or are we, in which case we would have a voltage rise, or we're going downstream with it. So for this, we need to look at the probable direction of current flow. So we know that we have already charged our battery up such that it's got a positive charge on this side and negative on the other. Furthermore, we know that our voltage source here is oriented effectively in the same direction as the capacitor. So we absolutely are going to have current flowing in that direction. I. Okay. So as we go from A to B around our Kirchhoff's voltage loop, we're going to experience a voltage rise plus I, which is of course a function of t. I'm not going to write it as such, times R. And to go from B back to ground, we're going positive to negative. So effectively we've got a backwards. This charged capacitor, as shown, is going to act again like another voltage source that's in backwards, minus V sub C. And that's going to equal 0 volts again. So here's this is our KVL expression. Okay, so now we just go ahead and we're going to acknowledge that this is constant. No variation with time. This is a perfect voltage source, no sagging. So we can assume that that won't change with time. And we can write an expression for V sub C as whatever the charge is on the capacitor. And we're going to remind ourselves that that's a function of time over C. So let's look at how this whole expression changes with time. So we're gonna apply our magical calculus again and take the first time derivative. So as we know, the time rate of change of 0 is 0. The time rate of change of something that doesn't change with time is 0. The time rate of change of current times resistance is di dt, which just simply is a mathematical way of saying the time rate of change of current, times R, minus this expression. So we're going to say, what is the time rate of change of that whole expression? Equals what? Well, we know the time rate of change of charge is current, but in this case we need to look at the magnitude and direction. So we've defined current as being the flow of charge counterclockwise. We define charge on the capacitor as being, a positive charge on this side. So if we say, okay, we want to express charge Q in terms of current. So if the charge here gets bigger, the flow of current in this direction gets smaller. If the charge here gets smaller, we are discharging the capacitor, the current gets bigger. In fact, you could say that it is the discharge, the reduction in charge, the negative time rate of change of charge on the capacitor that produces the current, that together with our negatively oriented battery. So we can say dq dt equals negative I. And that becomes very important in achieving the expression that we want down here. So we can say we're going back negative, so we've got that. We're looking at time rate of change. So the time rate of change of the voltage on across the capacitor is equal to negative I over C. And that all equals 0. So hey, we have something that should look very, very familiar. We end up with the same expression that we had when we were deriving this green curve. Well, we've got, di over I equals dt negative dt over rc. We're going to get the same expression. We can again write the current, this time it's going counterclockwise, is going to equal some constant times the exponent of negative t over rc. Now what's different? The initial conditions this time are really, really different. So we can say, well, at t equals 0, what's the current going to be? Well, when we first close this switch here, we're going to create, a big step voltage. So we're not going to get any resistance from our capacitor. It's simply going to act like another voltage source. Okay, how big was the voltage source? Well, we already charged it up to E back here in that first part of the step. So when we first close this switch, we have effectively a circuit that looks like this. We got, basically we got ground, and we've effectively got two, so I'll draw this like a capacitor. We could redraw the circuit like this, where we've got R, we've got C, but it's got a value initially of E, and we got a value of E here. So we could say that I is going to be equal to the resistance, oops, all right, this is a fraction, 1 over the resistance, Ohm's law, times not 1, but 2E. Because at the instant we close this switch, we've got two voltage sources basically aligned in the same direction, that can flow current through R. So there's our initial condition. So when t equals 0, I equals 2E over R. So that means that's what K has to be. So I'm going to move my whiteboard up here, give myself a little room. So I can say that I at any time is going to equal 2E over R times the exponent of negative t over RC. Okay. So that makes sense from a t equals 0 standpoint. We just used it to derive it. So what's going to happen as t gets really big? Well, this whole term will go to 0 and current will stop flowing. So we know that we will eventually reach a point where basically the capacitor becomes oppositely charged, it opposes the source, and then current stops. So that's the behavior we would expect. Now it's great that we have an expression again for current that's flowing through the capacitor during this time here, but what we're going to measure in our circuit is voltage. So we still need to go that extra mile and create a time-dependent expression for the voltage drop over the capacitor, since that's what we're going to measure in our circuit. So we're going to do the same thing we did before, and we're going to go back to our original KVL expression, except we're going to use this for I. Okay, so I'm going to refer to my notes here. And signs become very, very important now. So I'm going to start by just kind of getting rid of the zeros, and I'm going to rewrite this in terms of voltage drop over the capacitor on one side. I'm just going to move this to the other side. I'm going to add it to both sides of the equation. I'm going to say that's going to equal I plus E plus IR, excuse me. And this was a negative E. Very important. See, signs already. So now I'm going to put this term in for I. So I'm going to end up with the voltage drop over the capacitor, which means if I were to measure this again on a real circuit with a square wave, I would be measuring between point B and ground. So voltage drop over that capacitor is going to equal negative E, which is that source voltage, plus 2E over R exponent negative T over RC, where RC is our tau, time constant. Okay, and this is I times R. Okay, so E, negative E, IR is this whole term here. Okay, well, one thing we can notice is these two R's cancel, and we can say voltage at that point B at any time is equal to, we can factor out an E, negative 1 plus 2 exponent. So here it's the factor of 2 and the signs that are kind of making things a little bit different than they were when we were on that first cycle of our square wave. So here's our anytime expression. That means anytime, move our thing. Now when I say anytime, I mean anytime from this time to this time. So I'm only plotting this part of the curve. So my expression should show that if I put in t equals 0, I should get a positive E, and if I put in t equals infinity, which would indicate we've reached steady state, we're not changing with time, you know, my curve has gone flat down here, I should have a V sub c equal to negative E. So let's see if we pan out there. So if I put in 0 for t, this term is 1 because the exponent of 0 is 1, because exponent means e, the number e, raised to the power of 0. Well, that's 1 because anything raised to the power of 0 is 1. So I would get e times negative 1 plus 2, which is e. So that checks. So my initial condition is right. Next, I'm going to say, what if I let t equal infinity? Steady state, very, very long time. That everything's charged or as discharged as it's gonna get. Nothing's gonna change with time at that point. That's what steady state is. So I would put infinity in for t. So what do I know again about the negative exponent function? As t gets really, really big here, exponent of negative t, the curve looks like this. So as t gets really, really big in the positive direction, approaches infinity, exponent of negative t approaches 0. 0 times 2 is 0. E times negative 1 plus 0 is negative e, which is exactly what I would predict I would be measuring at this point in my square wave function. So that curve is something that I feel like I could trust, which is great. So I'm going to switch colors again because we've now done a lot with our aqua. Let's switch over back to red. Okay, so we're going to look again at our square wave function. So we got our picoscope, or I keep using my brand name. I'm looking at an oscilloscope trace of a square wave function here. So I've got my square wave function that I have imposed on my RC circuit, which, you know, maybe I could plot that if I wanted to. Maybe I plot that because you can plot your excitation signal if you have a two-channel. So you have voltage versus time. Okay, so this is whatever time. There's not really a 0 point because we're going to continue to plot. And I'm going to use blue for my, so this is, let me go back to red. This is my V imposed This is what's coming out of my my function generator, or if I'm using a picoscope, it's my AWG, arbitrary waveform generator. Okay, so that's what I'm applying. V applied, V imposed, applied, whatever. Okay, so if I look at V, the voltage drop across my capacitor that I'm measuring between that points B and ground, I'm going to get this. That's what I should see on my scope. And hopefully I come all the way to the point where it's not changing, or I should be, you know, decreasing the frequency and letting that capacitor get all the way charged and discharged. So if I wanted to confirm what R and C were, or what the product is, I can use, I'm going to draw it in purple here, I can say, well, I know that V sub C at any time is going to be equal to whatever my amplitude is of my applied signal that I'm applying to the whole circuit, which I could set on my picoscope and I will measure. So since this is going to go all the way flat, I will measure this. I won't trust what I applied because maybe I'll get some sag, but I'll measure what that maximum is. So this is max min that I measured times -1 plus 2 exponent -t over RC. Okay, I know that if I at t equals RC, V sub C is going to be equal to my E max min, my amplitude, times -1 plus 2 times the literal numeric value E, or exponent function raised to the power of 1. This has a numerical value which I can put in, and it is about, let me get the exact number. We can calculate this. So this will give us a basis of actually confirming our measurement. Actually, I need to look up what it is. Actually, we'll end up getting negative E. E raised to the -1, because we'll end up getting RC here, so we'll end up E to the -1. So 1, negative, enter exponent function, so it's about 0.36. So my measured voltage, which I can take right off of the Y scale of whatever my blue scale is on my oscilloscope plot, is equal to my E, just call it E max at this point, times -1 plus 2 times 0.3678, blah, blah, blah. And this will give me a number that corresponds to, which is relative to my maximum, and it's going to be a negative number. So if we have, a balanced signal here, so we'll go from whatever this is, we're going to go down, and as it turns out, we're going to go a set amount. So we have to 2 times that. I'm just plotting this out, 1 minus. So this will be equal to E max, in this case, times -0.2642, just doing the math. So we're going to end up with something down here. So if E max was 1, like this was 1 volt, we would end up with like somewhere around a -1/4 volt. So this would correspond to T equals R times C equals tau. So that would correspond to the time constant. So all we would have to do if we wanted to measure empirically the time constant, say we didn't know what R or C was, all we'd have to do is find the point on this curve, this 1/2 of our waveform, and say, okay, where is, at what time relative to the leading edge of our imposed square wave when we've gone flat and we're just starting to reverse and go down from this point here, at what time is the y value equal to whatever this maximum was times negative 0.2642. So if we find this value, then we just say, okay, what's the time corresponding to that? And we can measure that with our plot on our oscilloscope, and we'll get tau. And that characterizes the time constant of the circuit. So the bigger the tau is, the slower it responds, the smaller, the faster it responds. And then if we need to adjust it, we can change R or we can change C. And as we'll see in our actual circuit build portion of this demo, we know one or the other to a little bit better accuracy. Our capacitors, depending on how accurate, the precision of your capacitor, usually they're plus or minus 5%, which can add up to quite a bit when we're talking about a time constant. Whereas our resistors, as we'll see, we can measure what they actually are with our multimeter. So depending on the value you choose for R or C, your measured tau will be closer or further away than what your calculated value is. So you can actually decide. Theoretically, you could use different values of R and C to get the same tau. High resistor, low capacitor, or vice versa. Okay. Another way to get at this, and this is Tony Kuffel's method, and what it represents is basically a grab bag or a compendium of a lot of different scenarios for starting and ending in terms of charge versus time. And you could derive this with any configuration of circuits, provided that you know what the charge is on the capacitor at a given time from your starting time. You know what the resistor is, you know what the capacitor is, so that you would know the time constant. And this is called the universal time constant expression for an RC circuit. And what we're going to show is it's exactly what we derived with our two little switches. So this says the change in something you're measuring, which in this case we're going to say it's the change in the voltage drop over the capacitance. So start to finish, so we're talking a delta, is going to equal the final value minus the initial value. So final means steady state, start means whatever it was at time 0, times 1 minus e to the negative t over tau, which in our case is RC. So remembering that this is equal to tau for an RC circuit. Okay, so in our case where we were looking at imposed voltage signal like that, and we're looking at our discharging capacitor as being like this, V sub C in green. So V sub C final equals negative E. And V sub C start equals positive E. Oh, this color. Okay, so final negative E minus E. So we didn't get 0, which is good. That would indicate that it's always 0 and it never changes. Maybe had an open circuit. 1 minus e to the negative t over RC. Okay, so we would say that the change is equal to negative 2e times 1 minus negative t over RC. Okay, so the way we reconcile this with what we just calculated with our derivation is to remember this is changing. So this says, okay, what is the magnitude and direction of the difference in whatever we measured for RC at time 0, which was e, to any time? Okay, so we can say, well, let's start with t equals 0. At t equals 0, this expression is going to be 1. 1 minus 1 is 0. That means that time equals 0, there's been no change. That's exactly what we would expect because there's been no time for a change to occur. So let's take t to infinity. Let's look at steady state down here. Well, at steady state, this whole term would be 0. So that means the change in the voltage drop over the capacitor is negative 2e, because negative 2e times 1 minus 0 is negative 2e. Well, as it turns out, to go from here to here, our whiteboard just decided to not like us. We'll just finish this verbally while we wait for the whiteboard. Oh, there it is again. It's decided to cooperate with us for this last part. Okay. So our change, remember we're talking about a change in the voltage drop. So the change from whatever our initial value was, well, our initial value was E, so the change is negative 2E. So we can use this universal time constant expression the same way we would use the aqua, but we have to remember what our starting value was. So either way, we can identify that the value corresponding to a t equals RC is going to be somewhere around negative 0.26 whatever times our amplitude, and then we just have to find the time that corresponds to that and measure that on our circuit. So we are now armed with a time-dependent expression with a fixed point in time for which we have a multiplier on whatever voltage amplitude of our square wave signal that we want to apply, that we know when our voltage drop over our capacitor measured signal, we're going to bring it on whatever channel of our scope, when it reaches that value, we know that that would correspond to a t equals tau equals RC. So we can make that measurement and then see how it corresponds to whatever resistor or capacitor we've chosen, and maybe even identify which one of them if we know the other. So we are now armed with the mathematics to properly evaluate our measured signals from our built and measured circuit, and we can also warm up to do that and see these same expressions on a simulator. So that is it for this. Please stay tuned for 2 more videos. One where we'll make these measurements with Tina, our simulator on an RC circuit using the transient function, and then again with a real live measured circuit showing our picoscope plots.